Hey everyone, welcome back to my channel. Today we're going to tackle a hard problem on LeetCode. It's called Network Recovery Pathways. This problem requires us to find the maximum path score from node 0 to node n1 in a given network. With some constraints, we'll break down the problem, explain the intuition, and walk through the solution step by step. So, let's get started. The problem gives us a list of edges in the network, where each edge has a weight associated with it, and a list of Boolean values indicating whether each node is online or offline. We need to find the maximum path score, which is the minimum edge cost path from node 0 to node n1. Given that all intermediate nodes are online and the total recovery cost does not exceed a given value k. The core insight of this problem lies in understanding the conditions that make a path from node 0 to n1 valid. Think of it like a road trip, where you want to get from point A to point B, but you can only take roads that are open and have a certain level of quality. In this case, the roads are the edges in the network, and they have weights associated with them. We want to find the path that has the minimum total weight, or edge cost, while also making sure that all the nodes we pass through are online. This is similar to finding the shortest path in a graph, but with the added constraint of node online status. To solve this problem, we'll first construct a graph using the given edges and filter out nodes that are offline. Then, we'll use Dijkstra's algorithm to find the shortest path from node n1 to all other nodes, including node 0. This will give us the minimum edge cost path, and we can check if it's within the given recovery cost k. If it is, we'll perform a binary search to find the maximum path score among all valid paths. We'll keep adjusting the search range until we find the maximum path score. Now, let's take a look at the C++ code that implements this solution. We start by constructing the graph and filtering out offline nodes. We create an adjacency list representation of the graph, where each node is associated with a list of its neighbors and the weights of the edges. Then, we use a priority queue to implement Dijkstra's algorithm. We initialize the distance to node n1 as 0, and all other nodes as infinity. We keep pulling nodes out of the priority queue, updating their distances, and pushing their neighbors back into the queue. Once we've found the shortest path from node n1 to node 0, we check if it's within the given recovery cost k. If it is, we start the binary search. We keep adjusting the search range until we find the maximum path score. Let's go through the code line by line. We have a class solution with a function findMaxPathScore, which takes in the edges, online status, and the recovery cost k. We first construct the graph and filter out offline nodes. Then, we use Dijkstra's algorithm to find the shortest path from node n1 to all other nodes. We use a priority queue to keep track of the nodes with the minimum distance. We keep pulling nodes out of the queue, updating their distances, and pushing their neighbors back into the queue. Once we've found the shortest path, we start the binary search. We keep adjusting the search range until we find the maximum path score. The time complexity of this solution is O m log k plus O n log k, where m is the number of edges and n is the number of nodes. The time complexity is dominated by the binary search and Dijkstra's algorithm. The priority queue operations take O log n time, and we perform these operations m times for each iteration of the binary search. Additionally, the binary search itself takes O log k time. The space complexity is On plus m, where n is the number of nodes and m is the number of edges. The space complexity is primarily due to the adjacency list representation of the graph and the priority queue used in Dijkstra's algorithm. That's it for today's problem. Network recovery pathways. I hope you liked the explanation and the walkthrough of the solution. If you have any questions or comments, Please leave them below. Don't forget to like the video, subscribe, and comment your approach below.